When calculating the potential energy of an electrostatic system, we often assume the space around it is entirely empty. In practice, we must often account for a system of charges placed into an environment already permeated by a pre-existing electric field. We call this pre-existing environment the external field, represented by the variable E. This field is produced by sources completely external to the specific test charges we are studying. This creates a clear boundary for our calculations. When determining the potential energy of our localized system, we ignore the potential energy of the external sources that are generating the background field. These massive sources are considered mathematically distant at infinity, or securely held in place by other, unspecified forces, making their internal energy irrelevant to our local system. We assume our small test charges are too weak to significantly displace or affect these massive background sources when introduced to the field. Because the external generators are black-boxed, we only need to know the specific electric field E, or the resulting electrostatic potential V, that they produce at given points within our region of interest. Calculating potential energy in an external field focuses strictly on tracking the physical work done on our specific charges as they move through a localized pre-existing gradient. In this 3D coordinate system, equipotential lines represent our external electric field. We focus on point P, located by position vector r. We define the electrostatic potential infinitely far away as exactly 0. Imagine bringing a single test charge, Q, from that zero potential point at infinity to its final position at point P. Moving against the external field requires work. This work equals the charge Q multiplied by the potential V at position r. According to the work-energy theorem, this expended work is now stored as the potential energy of the charge Q. To see the scale of this energy, consider an electron. If an electron is accelerated across a potential difference of exactly 1 volt, it gains 1.6 times 10 to the negative 19 joules. This specific quantity is defined as 1 electron volt, or 1 eV, which is the standard energy unit in atomic and particle physics. While the energy of a single charge is a simple product of charge and local potential, a multi-charge system requires us to calculate the compounding work of assembly. Our goal is to determine the total potential energy of a two-charge system, Q1 and Q2, placed at specific positions R1 and R2 within an external field. The total potential energy equals the total work required to assemble these charges from infinity into their final configuration, one step at a time. Step 1 begins with a localized space containing only the external potential field. Our two target positions, R1 and R2, are currently empty. We bring the first charge, Q1, from infinity to its designated position at R1. Since Q1 is the first charge to arrive, it only does work against the pre-existing external field. The work done in this first step, W1, is the charge Q1 multiplied by the external potential at R1. This first piece of the system establishes a base energy level derived entirely from its relationship to the external environment. Now we move to step 2, focusing on position R2, where we will place Poseidon charge. The physical environment has changed. Charge Q1 now generates its own radial electric field. The potential at R2 is a superposition of the external field and Q1's field. We bring charge Q2 from infinity, locking it into R2. The total work done on Q2 consists of two distinct parts to account for both fields it must overcome. Part A is the work to overcome the background external field, which is Q2 multiplied by the external potential at R2. Part B is the work against Q1's electric field, with the distance between charges defined as R12, multiplying Q1's Coulomb potential by Q2 gives the mutual interaction work. Summing these parts defines the total work, W2, to add the second charge. Every subsequent charge added to a system increases the complexity of the assembly, as each new charge interacts with both the environment and its neighbors. The total potential energy, U, of the completed system is the sum of the work done in Step 1 and Step 2. This results in the final mathematical equation for the system. The first two terms represent the external field energy, banked strictly by existing within the outside environment. The third term represents the mutual interaction energy, banked by the charges pushing or pulling against each other. To remember this, simply consider that total system energy is the sum of the individual external energies plus the collective mutual interaction energy. We can test this formula by considering what happens if we remove the external electric field entirely. Without an external field, the external potential at both positions, V of R1 and V of R2, drops to 0. The three-term equation reduces, leaving only the mutual interaction energy term. This remaining term is the standard equation for the potential energy of two isolated point charges. Electrostatic potential energy provides a meticulous, exact accounting of the physical work required to assemble a system from infinity.